So now we will study chapter 5 about vector subspaces. And I make a remark. It's going to especially theorem because in section 2.4 we introduced the concept of the general vector spaces. So we will use several important theorems in that section for the study of the material in this chapter, especially theorem 2.4.10 and 2.4.12. All right, so the first section is about column, row, and the null spaces. Okay. Right, definition. A non-empty subset W of a vector space a vector space usually described by using a triplet. First of all, V is the set of all vectors, and the plus just the vector addition. So we have vector addition, and then we have scalar multiplication. Okay, so that we usually specify a vector space using such a triplet. Okay. If we know the vector addition, the definition of vector additions, and the scalar multiplication in the context, then we will use V itself to denote the vector space. Okay, so that is a convention used. Alright, so a non-empty subset W of a vector space is called a vector subspace. So we usually omit the vector of V if the W together with the vector addition plus and the scalar multiplication itself a vector space. Alright. So so we have a V here, vector space, and this vector space has vector addition and scalar multiplication. And also we look at a subset W here, and we find that the W together with the vector addition and schema application becomes to a vector space itself, then W is called a vector subspace of capital V. Okay. So for example, the vector addition should be closed in W. So any two vectors in W after the addition should be also a vector in W too. Also, any vector in W scale multiplied with a scalar should be a vector in W too. So you have to have a closure property. And so we can write it this way: plus and the same scale multiplication. If W is a subspace. Okay. So now an immediate theorem is needed to justify whether or not empty subset is a subspace or not. Okay. So now a non-empty set W of a vector space V plus it's a subspace of V if W is closed under the vector addition class and the scale multiplication from V. So closure property will be sufficient now. Alright? So closure property. The proof. The closure property imposed on W means two things. One is that for all U and V in W, U plus V must be also in W. Second, for all U in W and alpha real number, then alpha U should be in W. Right? So suppose we have this closure property. So that is the basic, right? To show a set of vector to be a vector space, you have to show that the closure property of addition, vector addition and scale multiplication should be true on W. So that's basic. And then we have 7 axioms to be justified. Okay? Remember, we have the 7 actions for a vector space in addition to the closure property. So now axiom 1 about the vector. So then let me say axiom 1 Axiom 1 is about commutativity, right? So take that. Commutativity of vector addition, right? The commutativity of vector addition, this one's okay, and axiom 2 associativity of the vector addition and axiom 5 distributive laws, and axiom 6 associativity of scalar multiplication, and the axiom 7, the unitary property. Okay? Alright, this 1, 2, 3, 4, 5. 5 makes sense. Or inherited from the vector space. Okay? Why? You can see the vector addition is that U plus V equal to V plus U. Alright, for all U, V. So when U and V are in W, they must be in V, right? Because W is a subset of V. So U, V should be in V, and because it's a vector space, so of course this is true. There is no the situation, and U plus V plus W is equal to U plus V plus W. Again, U, V, W in W, also in V. So this is true, of course. How about distributive laws? Distributive law says that alpha U plus V equal to alpha U plus alpha V. Of course it's true, because UV in W also in V. So it's true, and alpha plus beta U equal to alpha U plus beta U. Also true. Okay. Associativity of scalar multiplication, alpha beta U equal to alpha beta U. Of course true, because it's in V, it's true. Unitary, 1 U equal to U. Of course. So the 7 axioms are inherited from the original vector space. No problem. The only question is the axiom 3 and axiom 4. Do we have a zero vector for W? So we should check W, this is subset. This is subset contain a zero vector. Okay? If it has a closure property. So now we check. So axiom number 4. I'm sorry, axiom number 3. For axiom number 3, by the closure property, okay, 0 times u. Alright, since W is not empty, right? Alright, it's not empty, and so there is a vector, say u in W. Okay? Now by the closure property, zero scalar multiplier with u, right? Which is just zero vector, must be in W. Okay? So now that's W has a zero vector. Okay, maybe I have a code if we indicate that this zero vector is a zero vector for the original vector space V. And so that u plus 0 equal to u for all u in W. So the same zero vector for V is a zero vector for W. Of course, right? So we have axiom number 3. Okay. Maybe I would say, so W has a vector V such that this is true. Alright, so axiom 4. Axiom 4. By this closure property again, minus 1 u is in W, right, for all u in W. Okay? So we multiply with minus 1, right? So minus 1 u is in W because of the closure property here. Alright, and then minus 1 u so I check okay, so then minus 1 u plus u is equal to a 0 V. Right? Because this is true in V, right? Every u in W, also u is in V. And so we know that in V, minus u is the additive inverse of u already. So we know that. So this is true for all u. So we have axiom number 4. And then we have that. Okay, so a sufficient condition for a non-empty subset to be a subspace of V if W is closed under vector addition and scalar multiplication. So it's easy to check. Any questions? Okay, now the next theorem, 5.1.2, the span of a non-empty subset in a vector space it's a subspace of V. Okay. And the proof is that this is just theorem 2.420. If you go back to check our theorem 2.420b, you will see that the statement is still the same. So we have already proved that before. Okay? So I will not do it again. So the situation is here. So this is the vector space. Okay. Now you have some set. Say a set U here, arbitrary set. Then you will form the span. All right. So this is the span of U. Then span of U is a subspace of V. Okay. So the theorem 5.1.2 gives us a very convenient means to construct subspaces. You just pick up an arbitrary non-empty subset U here, and then you form the span. Form a span here, and then this span of U will be a subspace of V. Transport. So I combine two theorems in the textbook into one. So we let U and the W be subspace of a vector space V plus. Right, so suppose we have two subspaces. Then both U plus W defined to be U plus W. And U intersect W. are subspaces of V. Okay? Now, U plus M is called the sum of U and W. So the sum of two subspaces is again a subspace. The intersection of two subspaces is again a subspace of V. Okay? And the proof as an exercise. So please try to prove this theorem. At home, all right? So, and you just use the theorem 5.1.1. You just check that the sum of U and V is closed under vector addition and the vector scalar multiplication. And also, you have to show that the intersection is closed under vector addition and scalar multiplication. Okay? So it's easy to check. But I want to make a remark. Okay. In general, the union U of two subspaces U and V and U and W of a vector space V may not be a subspace. Cannot be a subspace of V. Okay. An example is here. Okay, so this is the plane. The plane is a vector space of two-dimensional vectors. And a line is a one-dimensional subspace. Okay, so this is a line here and a line here. So this is line 2, line 1. So a line passing the origin, the line passing origin is a subspace. Okay, so because they're passing the origin all here. So now L1 and L2 are subspaces. Because that you can see that if I add the two vectors on the line, they must be on the line 2. So that a vector addition is closed. And scalar multiplication also. If you have vector and you multiply with a real number, you will change the length only, right? So that it's still on the line. Okay. And so it's quite easy to know that these two lines are subspace of 2. But the union is not a subspace. Of R2. Why? Well, if you add the two vectors there, So for example, you add this vector and this vector here. So these two, this is u, and this one is v, and the sum it's so the sum will be is here. So this is the u plus v. But you can see that this vector is not on L1, right? Not on L2. So that the vector addition is not closed under this union, not closed. So in general, if you just take the union of two subspaces, then this union is not a subspace. But for intersection of two subspaces, then this intersection is a subset too. Okay, and also true for the sum of two subspaces. Yeah. Alright, let's recall the notion of function. So we let f is the function from a set A to set B. The image f u of a subset u of the domain A. So U is a subset of the domain A. Now f of U is the image of U and is defined to be okay. So it's just the collection of all the values of the function f at each element u. So you see that f of u is a subset of the codomain. Okay, a subset of the codomain. And we would, the inverse image of a subset W of the codomain B is defined in this way F. Okay, the inverse image of a subset W of the codomain is defined to be all the elements in A such that f of x is in W. So suppose that okay, and so this is domain A, consists of 5 elements. the codomain B consists of 4 elements, and the mapping F, yeah. All right, so the F of ABC, right. F of ABC is a set of A, of B, and F of C. So what is that? F of A is 1, F of C is 1, right? So it's 1 and 4 and 1. So that is 1 and 4. Okay, 1 and 4 here. Maybe I changed my mind a little bit. Equals to 2. Sorry. I'm sorry. I got it's much more interesting. So the image of this set U is 1 and 4. Alright, so this is a subset of the codomain. Now, the inverse image of say 1 and 2. Okay? So what is that? We want to collect all the elements in the domain such that the image, their value will be in the set W. Now, we will see for 1, we see that A and B will go to 1. So now we have A and C here. How about 2? Well, we have E here. Alright, so the inverse image is a subset of the domain. We can 3. Right? What is the inverse image of the set? Consists only 3. What is that? None of them, right? So it's the empty set. Empty set is also a subset of A by definition. Any questions about inverse images? So we define inverse image only for subset of the codomain. Okay? Only subset of codomain. The next theorem, 5.1.56 plus 6, let T be a linear transformation from a vector space to another, to a vector space W. Right. The T is a linear transformation. The image P U of a subspace U of V okay, Okay, so the image of a subspace U of V is a subspace of W of the codomain. And the inverse image P inverse Z of a subspace Z of the codomain W is a subspace of the domain V. So we have this is V, this is W. Okay, given a subset V here. Now we map to here. Now, if U is subspace, then TU, if U is a subspace of V, then its image TU is a subspace of W. A subspace Z of W, when we take its inverse image, then the inverse image of Z is also a subspace of domain V. So for linear transformation, so if the function is a linear transformation, then we have a nice property preserving effect. Okay, so subspace goes to subspace, but in W, and the subspace in W, do the inverse mapping, goes to subspace in V. Alright, so this to prove here. So we let W the prime be U. Alright, so we want to show that if U is a subspace, then TU, the image of U is a subspace of W. So now let W, the prime be in here. Okay, so then there exists U prime in U such that W is the image of U and the prime is the image of U prime. Okay? So now we check the sum, right, of these two elements accumulated in the image of U. And this is TU plus TU prime. Now, by linearity of the linear transformation T, so this is T U plus U prime. Right? Since U is a subspace of V, U plus U prime is also in U. So U is closed under vector addition. Alright, so the sum is in U. Now, so this implies that f of this implies that W plus W prime, which is the image, is in TU. Okay? So we prove that whenever we have two vectors in the image of U, their sum is also in the image of U. Okay? So the image of U is closed under vector addition. And for all alpha, alpha W is equal to alpha TU is equal to T alpha U. And this is in TU since alpha U is in U. Because U is a subspace, right? So it is closed under scalar multiplication. Okay, and so we start with W in TU. We find that alpha W is also in TU. So TU is closed under scalar multiplication. So the conclusion is that TU is closed under vector addition and scalar multiplication. Alright, so by theorem 5.1.1, TU is a subspace of W. Next, we want to show that the inverse image P inverse Z of a subspace Z in W is also a subspace of V. So we let X, Y, and Z. I'm sorry. We plug in inverse of Z. Right? So we consider two vectors in the inverse image of Z. Right? We consider them. So that so there exists X and X prime in Z such that TV equal to X and TV prime equal to X prime. This is the definition of inverse image. Okay. So V and V prime is in the inverse image of Z. It's because that I think I can make it much simpler. Then TV and the TV prime must be in Z. So their image should be in Z. This is the definition of inverse image. Okay. So then, last, we have T U plus T U prime is in Z because Z is a subspace. So this implies that T prime, okay? So this implies that V plus V prime is in the inverse of V by definition. Because the image of the sum is in Z, so that the sum must be in the inverse image of by definition. Alright, so we see, starting with two vectors in the image of Z, we find that their sum is also in the image of Z. Also, alpha T U is in Z. Okay? Because that Z is a subspace of W, so it occurs under scalar multiplication. And so this is P alpha U is in Z. Right? So when P alpha V is in Z, that means that alpha V is in the inverse of Z. Okay, so once again, you see that for any vector in the inverse image of Z, it occurs under scalar multiplication. Alright. So inverse of Z is closed under vector addition and scalar multiplication. So again, by theorem 5.1.1, the inverse image of Z is a subspace of the domain B. Okay, so this is the end of proof. Alright, so let's take a break for 5 minutes. The range of PV is the subspace of the codomain W. The proof is just an application of the previous theorem. We know that TV is the image of V itself. Okay? And V is the subspace of V. So, or TV is the image of a subspace V of V. Okay? Because V is a spatial subspace of itself. And the kernel of P is what? Is the inverse image of the zero vector of W. Okay? Is the inverse image of a subspace subspace of W. Because if we consider only the zero vector, so this subset consists of only one vector, which is 0. Then it's called the trivial subspace. The trivial subspace, of course, this one is a subspace of the codomain. Alright, so TV is the image of a subspace V of V. And kernel T is the inverse image of a subspace of W. So by theorem 5.1. 5 plus 6. TV is the subspace of W, and the kernel T is a subspace of V. Do you have any question about this fact? Kernel P is indeed the inverse image of this spatial subspace. What is that? This is all the vector such that TV go to the zero vector. Remember that? The kernel is all the vectors in the domain such that its image, its value is the zero vector W. Alright, so that is the definition of kernel. And this is exactly the inverse image of this spatial subspace. Alright, the row space OWA of an M times N matrix A is the span of the set of rows in A. So row space is the subspace spanned by all the rows in A. Okay? And you can see that, okay? And the column space COLA of an M times N matrix A is the span of the set of columns A. Okay? Now by theorem 5.1.2, okay, by theorem 1.1.2, the rows of A, because it's the span of all row vectors, the row space is a subspace of, and the dimension of the row, right, is n, so that it's a subset of arc, and the column space of A is a subspace of R n. Any questions? Now we first investigate row space of a matrix, and we will have a theorem 5.1.9. It says that if two matrices are row equivalent to each other, then they have the same row space. Okay, so if we know two matrices are called row equivalent, if we can start from one matrix and applying a sequence of elementary row operations on that matrix to obtain another matrix. That is our definition of row equivalence in chapter 1. Okay? So to prove that, okay, we first prove special cases. Right? Case 1. Alright, so consider two row equivalent M times N matrices A and B. Alright, so we consider two row equivalent M times N matrix. And case 1, B is obtained from A by replacing the ith row AI, the ith row I of A with I plus alpha j. So suppose that B is obtained by just applying replacement on A. Okay. I.e., A is 1, I, J, M, and B is obtained from A by applying replacement I plus alpha J M. All right, so V is in the row space of B. If and only if, so V is a vector in the row space of B, if and only V can be written as alpha 1 R1 plus alpha I, I plus alpha Rj plus alpha J, Rj plus alpha M, Rm. Alright, so V is a linear combination of the M rows of B. So this is the M rows of B. And so that we can have alpha 1 plus alpha I plus alpha plus alpha J plus alpha M, Rm. So it's a linear combination of the M rows of A. So this implies that V is in the row space of A. Okay. It's obvious to see that. So we just move the term to here, combine together. So that we prove that whenever V is a vector in the row space B, we show that V is also a vector in the row space A. So we have that row space of B contained in the row space of A. Similarly, we start with the row space of A. So V is only V is alpha 1 R1 plus alpha I plus alpha J plus alpha M M. So V is in the row space of A, then V can be written as a linear combination of the rows of A. But we can do it the way that alpha I plus alpha J. Alright, so we add a vector here, and then we do something that we have alpha J minus alpha I alpha J here, plus alpha M M. So we add a term here and subtract the same term. Right. And from here you see that this implies that V is in the row space of B. Because V R1, Ri plus alpha Rj is the jth row of B. And here this is the ith row of B. This is the same, the jth row of B. And it's also a scalar here. Alpha J minus alpha I times alpha is also a scalar. Alright, so we prove that, and so that row space of A contained in row space of B. Alright, so from this one and this one, the conclusion is that row space of A is equal to row space of B. Okay, so we prove the special case one, that if B can be obtained from A by applying just one replacement, then row space of A is equal to row space of B. So they have the same row space. Okay. The second case is about scaling. B is obtained from A by scaling the ith row of A with alpha. Alright? So that again, now this time B becomes true not equal to 0. Because scaling, we usually scale a non-zero scalar. So we have okay. And so a vector in the row space of B, you can only be equal to alpha 1 R1 plus plus alpha I Ri plus alpha M M. Okay, and so this is alpha 1 R1 plus plus alpha I alpha by associated law Ri plus plus alpha M Rm. And look at here, the CV is a linear combination of R1, R2, Ri up to Rm. So they are rows of A. So this is the space in the row space of A. Okay. All right, and so so row space of B is contained in the row space of A. Also, when B is in the row space of A, if and only if V can be written as alpha 1 R1 plus alpha I plus alpha M M. And so this one we can write as alpha I divided by alpha I plus. Okay? So now this row becomes a row, the ith row of B here. Okay, and it's, again it's scalar. So this implies that V is in the row space of B. So that row space of A is contained in the row space of B. Right? And then we have this one and this one. So again, row space of A is equal to row space of B. Alright, case 3. B is obtained from A by exchanging the ith row and the jth row of A. So in this case, the B becomes to R1 Rj Ri M. Here is the ith row, here is the jth row. So we exchange the ith and jth row of A to obtain the B matrix. But the row space of A is the span by definition of the set of R1 Ri Rj Rm. Okay? But the row space of A is just the span of the rows of A. Now, because it's a set, so we exchange the position of I and J, so we will get the same set. expensive. And this is exactly the row space of B. Right? So we have done for the case 3. Now for the general case, in general, there is a sequence of elementary matrices E1, E2 up to Ek such that B is right. So B is obtained from A by applying a sequence of elementary row operations. Okay? Where EI is an elementary matrix corresponding to one of the type three types of elementary row operation. Okay, so we have that. So now row space of A is the same as the row space of E1A. Okay? Because just by one elementary operation, we have either case 1, case 2, case 3, and then so they have the same row space, right? And again, is equal to the row space of U1A. Right? So you apply another elementary row operation, you will not change the row space. Right? And then you keep doing so. So finally, you get the row space of EK, E2, E1A. Okay. And which is just exactly B. Okay, we're done. Okay, and a trivial theorem. So trivial. Anyway, the column in the textbook, the column space of an M times N matrix A is the set. So the column of A is actually AX. X is in R and okay. So of course this is in I. So the column space is a linear combination of the n columns of the matrix A. Such that okay, and this is obvious, so I think I don't need to provide proof. Okay. Just state it. Before we leave this section, I'd like to make a remark here. Let U be the reduced row echelon form. Of an n times n matrix. While the row space of U is equal to the row space of A, because U and A are row equivalent to each other. So from the previous theorem, they have the same row space. But the column space of A may not equal to the column space of U. Okay? So we take an example. A it's 1 1 1 1 1 1. Okay, and it's reduced echelon form is here. So A and U has the same row space by our theorem, right? Now look at the column space of A. What is that? The column space of A is T 1 1 1 such as T and R. But the column space of U is T 1 0 0. And look at these two. Of course, they are not equal, right? So it seems that to find row reduced echelon form is useless. Seems useless, right? In terms of the column space of A. But it turns out that the information contained in U has something to do with the column space of A. All right. So I make a remark here, but we will show that column space A is the span of the set of pivot columns in A. Okay, so we will show that. For example, this is a pivot column because we have pivot here. So the column space is spanned by only the first column. Okay. Of course, column space of A is the span of the set of all columns. But you can reduce the column, the number of columns, just saying that the column space of A is the span, all right, of the set of only pivot columns, only for those columns contain a pivot. And that will give you more information about that. And we will show that later on. Okay, so we step into the second section, and a very important section in linear algebra. Okay, so we will discuss basis and dimensions. Okay, so first of all, a definition. In a vector space, V, right? A linearly independent set which spans V, right? So a linearly independent set, and this set spans the whole vector space. Is called a basis for V. Remark: a basis for a vector space can be finite, can be a finite set or an infinite set of vectors in V. Okay. Let's take a couple of examples. If P, right? P, the set of all polynomials. So the degree is not can be any degree. Okay. Then P, the set B1 P square Pn is a basis for P. Right? And you can see this basis is an infinite set. Okay, consists of all monomial. Right? So, so we have to provide a proof for that. Okay. So first of all, a polynomial Pp in P is written as so Pp A0 plus A1P plus A2P square plus ANPN, okay, which is a linear combination, right? Which is a linear combination of vectors 1 P square up to Pn. Thus, we know P contained in the span of the set V. Okay? So you can see every polynomial, we usually recommend it as a linear combination of the vectors here. So that P, the set, the vector space of all the polynomials, is contained in the span of B. But of course, the span of B must be a subspace of the vector, of the original vector space P by theorem 5.1.2, right? That we just proved that before. Yeah. So we have so the span of P is the span of B, right? So the set span the vector space. Right. This is the first requirement. The second requirement is we have to show that B is a linearly independent set. Right? Okay. So that. The second part. Okay. So now we consider a linear relation on B, right? So we have alpha 0, 1 P plus alpha M, which is equal to the 0 vector. So this is the 0 polynomial. Okay? So suppose we have a linear relation. So it's a linear combination of the first m plus 1 monomial. Okay? So we consider. And we say that this is the 0 polynomial. Then by definition, a 0 polynomial, okay, has all 0 coefficients. So i.e., we have alpha 0 equal to alpha 1 equal to alpha m equal to 0. So that's B is a linearly independent set. Okay. So B is a basis for P. Okay. Okay. I have another example, but I don't have enough time, so I decided to provide a theorem. So now this is just one example. I'm sorry. The other example is simple one, but I think I'll just take one example. Now, so I would like to prove the theorem here. The set of columns, right, of any n times n invertible matrix Alright? It's a basis for Rn. Okay, so this is very interesting. So we can find a basis for Rn from n columns of any n by n invertible matrix. Okay, so that is the idea. Okay, so let A1, A2, An be an n times n invertible matrix. Alright, so and we want to show that the n columns is a basis for Rn. The column space CLLA of A is just CLLA okay, so of course that is a subspace of Rn, of course. Because it's a span of all columns of A, right? So it must be a subspace of N. Now for each B in Rn, we have x equal to A inverse B in Rn such that Ax, right? So we can find a vector x, say the A inverse multiplied with B. This must be a vector in Rn. So now we apply Ax here. We have A inverse B, which is B. So we find a vector x in Rn such that Ax equal to B. So this implies that B is in the column space of A. Right, so we just, by construction, we just say that B is in here. Why B is in here? Because we can find an x in Rn such that Ax equal to B. This is exactly what we have done here. Okay? Any questions? So exactly. Okay, and so that Rn is this proves that Rn is contained in the column space of A. And from that, so we have that the Rn is equal to alright, and so is the span of alright, so we know that the set of all columns of A span the whole vector space Rn. This is the first requirement. The second requirement for a basis is that we have to show that the set of all columns are linearly independent. Now if alpha 1, A1 plus alpha 2, A2 plus alpha n, An equal to 0. Alright, so consider a linear relation on the set of all column vectors of A. Alright, so consider linear relation. This is a linear relation there. Okay, then we have A1 So we have this equation, and by multiplying their inverse, the inverse of A so we have that alpha, the vector, the coefficient vector is equal to 0. So that makes us alpha 1 equal to alpha 2. So it's a linearly independent set. Okay. So now we show that the set of all columns is linearly independent. And we already show that this set spans the whole vector space Rn. So of course, so the conclusion is that A1, A2 up to An is a basis for Rn of the vector. Okay, so finish the proof. Yeah. Okay, so the theorem is quite useful because when we look at an irreversible n by n matrices, then the n columns of the matrix will be a basis for Rn. Okay, so I stop here.